let's get started. I'm pleased to see some people came back for more, for another mathematics option. Right, so this is 2024 Mathematical Methods 2. It is open to first, second and third years. If you are here in your first year, that means you've done the Chem 1047. If you're in the second year, means you've either done my option math in your first year or Andrea Russell's math. And if you're a third year, it's generally open. That means you're probably interested in some kind of physical chemistry or spectroscopy or computational chemistry, and you need the mathematics that comes with it. Now, although I will be teaching you what is apparently mathematics, this course is really the foundation for quantum mechanics and spectroscopy. So if you're going to do things like quantum computing, like machine learning, chemical databases, spectroscopy, particularly magnetic resonance, I will save the first years a great amount of hassle when quantum mechanics hits you in the second year. You will be well prepared, much more prepared than your peers. To the second years, you will get a lot of the quantum mechanics from this course that will then arrive in your spectroscopy courses. And to the second and third years, hopefully this will be some retrospective explanation as to what on earth that was that Chris Harris was talking about when he was introducing field theory and such. So this all goes with the trend of mathematics and computing becoming ever more important in chemistry. These days, synthetic organic chemists don't even begin their synthesis until they're convinced that what they're proposing to do is workable inside a computer because of the expense, the workload, and everything that's associated with it. And so I will give you the infrastructure for all of those areas of chemistry that essentially require mathematics, which is pretty much all of them these days. So what we start with is a much deeper look at vectors and matrices. You have had three-dimensional vectors and 3x3 matrices in your elementary mathematics course. We will today introduce the subject as it is done in serious mathematics through a concept of multidimensional, arbitrary dimensional vector spaces. But before I begin with the formalities, I thought I'd give you an overview of where this came from. Now, the subject was growing in mathematics itself since about the 17th century, but it was only around 1905, when quantum mechanics arrived, that people realized that the matter is in fact central. And it happened because when quantum mechanics turned up, it was quite shocking, really, even to its creators, very counterintuitive, because very high-dimensional spaces were involved, functional spaces, and so on. In particular, the following types of things started making appearance all over science, right? From social science all the way to radio astronomy. You would have things like A11 x1 plus A12 x2 plus so on A1 n equals some number. So here A's are the numbers and X's are the variables, and then you would have A12 A21 x1 plus A22 x2 plus so on A2n equals B2. So another equation of the same type, and the same will continue all the way to A1 x1 and x2 and so on xn equals bn. And the chemical or physical nature of these coefficients and these numbers can vary an awful lot. If you are doing chemistry, then x's will be concentrations. And if you have them with some coefficients in front, like those that occur in chemical reactions, you will be looking, for example, in this case, at the conservation of matter. So your concentrations taken with some coefficients should add up to a certain total concentration. If you're looking at radio astronomy, then what you would have is this list of x, x1, x2, x3, xn, would be the pixels of an image that you would like to see. These will be the pixels that the instrument actually has recorded, and the coefficients A would be the response function of the instrument that converts one image into the other. If you are dealing with magnetic resonance imaging in medicine, then the X would be the raw signal that the tomographer records, and B would be the image of your brain, for example. And then in quantum mechanics, these would be relationships between some stationary states of some quantum system. But they all look exactly the same. And you have seen instances of such equations like 2x plus y equals 3, 5x plus 3y equals minus 7. Here the variables are x and y, and the numbers are numbers. And here we produced a uniform set of notations. Instead of x, y, z, we have x1, x2, all the way to xn. And in modern chemistry, n can be in the tens of thousands. So those of you in the second and third year who did chemical theory probably encountered 6x6 systems of equations for things like benzene. But practically, if we're dealing with realistic accuracy calculations these days in chemistry, and will be in the tens of thousands. So we are dealing with monstrous systems of equations that we would rather not have to solve by substitution. What we have here is relatively straightforward, you know how to do it, but when you have something like that, life's too short to try these things by hand. Then people started thinking, well, okay, how do we calculate that? And it quickly turned out that computers are singularly bad at analytical calculations. You have Mathematica these days that can kind of handle it, but if you were looking at 1950s, 1960s, computers barely even existed, and they were certainly extremely bad at analytical simplification. So what people started doing is they transformed the notation into tables of numbers instead, that the computers then were actually pretty good at. So A11, A12, A1m, A21, A22n, so on, A1, A2, An. Then we write the matrix. It is called a matrix of coefficients like this. We write the variables in a column next to it. x1, x2, xn, and we write the free terms in there, b1, b2, and so on, bn, z. Now this notation is more straightforward because a computer is quite good at storing arrays of numbers and accessing them sequentially and manipulating them and multiplying them. And if you look at this notation, we can introduce the notion of a product in here. That simply means we take this entire array, we turn it around and we multiply it into this line, and we sum it up. The result will be the first line of that system of equations. If we take that array again, turn it, multiply it into this, sum it up, that's what we have there. You can see that the operation becomes patternable and repeatable, easy to program. This is something that computer would be extremely good at. And then we can introduce the identity of operations that is element by element identity. So it's not just between two numbers, but between two vectors, meaning that the arrays are equal element by element. And then a further layer of simplification for this is if we then call this enormous thing A, and it's usually bold capitals that are used in textbooks and scientific papers, we call that X, and we call that B, then you can see that the notation simplifies dramatically. Instead of having to write all of that horror, we now have a type of notation that doesn't even depend on how many elements we have in those arrays. It could be 10 by 10, could be 10,000 by 10,000. Nothing changes at this level. And then this kind of notation that's completely dimension agnostic and actually agnostic really to what is inside x, b, and a. These could be vectors, these could be functions, as you will see in due course when we start dealing with those things. So this compact matrix vector notation is the subject of our lecture today. And it was about 1960s that the whole of physics, chemistry, and related disciplines have switched from there, which pretty much goes to ancient Greeks, right, to this, which is singularly well adapted for computers. And in modern programming languages like Mathematica or MATLAB, engineering computing systems, you will notice that actually matrices and vectors are elementary data types. So variables, by definition in MATLAB, are in fact matrices. And so this simplified notation is carried through the programming languages, where you can multiply a matrix by a vector, for example, in just 3 symbols of what is a very powerful programming language. But all right, enough of this. You have seen this in one way or another, either at school or in your previous courses. What concerns us today is a slightly more serious exposition of what it really means to be a vector in mathematics. So we will introduce the first topic on the agenda today, is vector spaces. So the formal definition is a set being O1 field. Those of you who attended the first semester of this module know what a number field is. For those who didn't, it's just the place where numbers live, real or complex. F is called a space. A number of conditions are satisfied. So the first thing that should happen is any 2 vectors living in that space, we should be able to add. Not only that, but the result should also be a vector. At a simple level, you know how that happens. You know, 1, 1 plus 1, 2 equals 2, 3. If we take 2 vectors and add them up, we should get the vector of the same dimension. Now, formally, mathematically, this means that the set of vectors is closed under the addition operation. So if we say for any A and B belonging to V, so this symbol is for any, some of you know this already, any element A and any element B belonging to that set, we must have A plus B belonging to the same set. The formal statement that the set is closed under addition. It should also be closed under multiplication by a number. If we take 1, 2, and multiply the whole thing by 3, we do that element by element, 3, 6. So the set must likewise be closed under multiplication by some scalar. So, for any element A inside B, and for any element alpha inside F, which means A is a vector and alpha is a number, alpha A must be inside B. So any vector multiplied by a number is again a vector of the same dimension. Various trivial things that are unimportant to us because we are physicists and chemists, but important to mathematicians because objects exist in mathematics where this isn't true. We should have associativity and commutativity. So for any A and B, and actually C, I think, so for A and B for now, inside B we must have A plus B equals B plus A. This is trivially true for vectors, but if you, for example, try to add rotations in that way, you would realize that rotations cannot be interchanged. If you have one rotation in 3-dimensional space and then the other, then if you apply one then the other, or apply the other then the one the compositions are generally to different rotations. So there exists objects even in simple geometry where this is not the case, but the property is called commutativity. We should also have associativity for any A, B, and C inside V. We must have A plus B plus C with brackets this way equal to A plus B plus C with brackets back. So the result of an addition should not depend on the order in which we perform that addition. And this is called associativity. And we will encounter things later in this course which are actually not commutative and not associative. Quantum mechanics in particular is quite related to this. You will see that in magnetic resonance course rather a lot, where the notion of a commutator with respect to multiplication rather than addition in this case is featured quite heavily. Now what we must also have in each space, again in retrospect perhaps a trivial observation, but the point of this is not so much to make trivial observations as to introduce the corresponding notation and the way of thinking about vector spaces that mathematicians have. We must have what's called a zero element. There exists a unique zero element inside V such that A plus 0 is the same as 0 plus A is the same as A. So there must be a unique element which when you add to anything just doesn't change it. For each element there should likewise be what we call an inverse, an additive inverse. For A inside V, there should exist something we will call a minus A, such that A plus minus A is 0. Roughly speaking, for every vector in a space, there should be a vector pointing in the opposite direction that when you add it to it would reduce to 0. In most cases in geometry this is trivially true, but for example in dissipative quantum systems, because dissipation is an irreversible process, let's say you have some dynamics like a pendulum swinging, and some friction on that pendulum, when you reverse the direction of time, the pendulum would just swing backwards, but you cannot reverse the friction because you would violate the energy conservation. So there are some processes in physics that are reversible and other processes that are not reversible. Geometrically speaking, however, we can demand for each vector a reversibility, and that is an essential condition for that to be a vector space. And then associativity and distributivity should likewise hold for the multiplication by scalars. We should be able to multiply scalars in any order. For any A inside V, and for any alpha and beta inside F, real numbers, complex numbers, whatever it is, we should have alpha, beta times A being equal to alpha, beta, A. So we should be able to multiply scalars into our vector in any order. Again, trivially true in the simple geometric interpretation, but not necessarily so for the more interesting types of sets that we will later encounter. And finally, it's a fairly long list of properties that I have in your handout, but essentially this says that all the bracket opening rules must be observed. So all the bracket rules. And I have them listed in your handout, all work as usual. Okay, so let us now demonstrate that, for example, vectors in 3 dimensions satisfy this. In the case of R3, 3-dimensional Cartesian space in which you and I live, just 3 vectors. If we take 2, 3 vectors and add them together, it's the same type of vector. Our numbers are real numbers. We know that we can multiply a vector by a number. And then all the other properties just follow through. However, if we were to, for example, require that we switch to the special relativity space, so where we have R3 with time, and ask if the set of all permitted directions in special relativity is a space, then it would not necessarily be, because, for example, condition D would be violated. There will be a physically permissible travel direction forward in time, but of course backward in time we cannot move. And so not for each vector we would have physically permissible inverses. So even in geometry, right, as soon as you introduce unidirectional processes, certain sets of vectors are no longer spaces. So that is the definition of space. We should now start building infrastructure on it. This space needn't be 3-dimensional. It could be 25-dimensional, it could be infinite-dimensional. And we will actually encounter examples of infinite-dimensional spaces. And so now that we've introduced it, we really should put some furniture into it. We should introduce the notion of distance, the notion of angle, various relations between objects in what is substantially something that vaguely resembles what we know from conventional geometry, but might differ from it in some essential aspects, particularly if the field of scalars becomes complex. We are used to geometry that is real, but quantum mechanics unfortunately begs to differ, and in quantum mechanics the coefficients are nearly always complex. And so we should now introduce everything from scratch to account for the possibility of things being rather more complicated than what we're used to. Okay, so elementary operations that we can do are much the same, so addition and multiplication by a scalar. I will remind you that there is an operation called a transpose, where you have A1, A2, and so on, An. Little t gets you into a row, A1, A2, An. And if you put another transpose on it, it will rotate back. So, but in the same order. Do another transpose, you go back. And then for complex situations, we need to introduce an operation that is very important in quantum mechanics. It occurs there, well, in almost any equation you can think of. It's called a conjugate transpose. And it's denoted with a dagger, like this. And this means transpose and complex conjugate every element. And that means a complex conjugation. And I will remind you that complex conjugation is when you take every instance of I and replace it with a minus I. Like 1 plus 2 conjugate. This is quite important when we start introducing the notion of links. Okay, so that's the formal definition of a space and the operations, the addition, the multiplication by a scalar, the transpose, and the conjugate transpose that we need to know about. The second item for today of general significance is called the linear combination. Or more specifically, in the second years and the third years will by now have come across molecular orbital theory, which has a wonderful abbreviation, MOLCK. Molecular orbitals as linear combinations of atomic orbitals. You must have suffered through that the second and third year, and now I'll tell you what it is. So, a linear combination in mathematics is the object of the following type. and x1, x2, and xn are vectors, and that is a vector. So, a vector y is called a linear combination of vectors x1, x2, all the way to xn, if it can be expressed in this way, where alphas are coefficients that come from your numbers, real, complex, whatever they are. This is quite important because such combinations occur an awful lot in chemistry. If this is your molecular orbital, for example, the highest occupied molecular orbital in some benzene molecule, then x's will be the atomic orbitals corresponding to individual carbons and protons that you have there. And a very important question is about uniqueness of such expansions. Given the vectors x1, x2, and xn, under what circumstances is this expression unique? And it is unique if these vectors x1, x2, and xn are what's called linearly independent. And the definition of that is as follows. Vectors x1, x2, xn are called linearly independent if none of them is a linear combination of others. Let's have some examples of linearly dependent and linearly independent sets of vectors. If I, for example, say, okay, x1 in two-dimensional space, 5, 3, x2 is 1, and x3 is 7, 5. Then the question is, okay, is this set of vectors linearly dependent or linearly independent? Well, we can say, by just staring at it long enough, that if we take x1 and add to it two instances of x2, then we will have x3. So x3 is x1 plus 2x2. In this case, by direct inspection, there are better methods of doing that. I will introduce them in the next lecture. So x3 is clearly a linear combination of x1 and x2 with coefficient 1 and coefficient 2 in this case, and therefore the set is linearly dependent. Then if we pick up something else, for example in 3 dimensions, in R3, if we have x1 equals 1, 0, 0, and x2 is 0, 1, 0, x3 is 0, 0, 1. Well, you know perfectly well that these are the 3 Cartesian axes, x, y, and z, and you intuitively understand that those directions in 3-dimensional space are independent from one another. And indeed, it's quite plain in here that no matter which coefficients we put in front of x2 and x3, there is no way to obtain an x1 from them because the first element is 0 in both cases. So this set of vectors is linearly dependent, and that set of vectors is linearly independent. And they will eventually come to play a fundamentally different role in the mathematics that we will then be building from this. Okay, so this is linear combinations. So we now see how to make vectors from other vectors. We make linear combinations. And as a part of our furniture building effort, let us now introduce, or rather perhaps generalize, the notion of distance and angle, but for spaces of dimensions that might be significantly bigger than 2 or 3. Let's first remind ourselves how we introduce angles and distances into the more conventional spaces that we have. Distance was quite easy. We were just calculating the length of that vector using substantially Pythagoras' theorem. I will remind you that in R3 we had the length of the vector R, which was x, y, z. It was x squared plus y squared plus z squared root. Well, it's actually quite straightforward to generalize this. If instead of x, y, z, we have x1, x2, x3, and so on, we can say that the norm of a multidimensional vector, note the double vertical lines, norm in mathematics is a generalization of length. And that's a norm will be x1 squared plus x2 squared plus so on, however many dimensions we have there, x and so on. That is norm, and this is for real vectors. Length, by definition, is something positive and real. As you can imagine, if our vector suddenly has complex elements, then we will have a problem, because this number might be complex, this number may be negative, in which case our length will become imaginary, which is not a good idea. And so for the complex case, this is generalized in the following way. If x is a complex item, then we have the following. It's x1, xy conjugate plus x2, x2 conjugate plus so on, x and conjugate. And that's the complex case. These two things are more similar than they appear. Really, the intention is to make sure that each of these things are real. And if you remember from complex numbers, if we have, for example, 1 plus 2i times its conjugate, 1 minus 2i, let's just multiply it out for illustration purposes to really see. This is 1 plus 2i minus 2i, and then you have minus 2 squared I squared cancels the minus, and so it's plus 4, 2i cancels 2i, and so this is 5, and it's real. And it's generally the case that any complex number times its conjugate produces a real number. So really the intention of this, it has a more serious geometric rationale. How do you introduce norms on complex spaces, but we don't really have the time in this course to go deeply into this. The intention here is to make sure that the number that comes out under the root is real and positive, and it will be as a result of this. And then when we take the root, we get a positive real number. And the only way we get a 0 is, in this case, if all of these elements are 0. So the norm, we can now produce a more general definition of it, is as follows. The norm of x is the square root of sum over k, so all elements of x, k equals 1 to n, x, k complex conjugate, or equivalently, if you remember the definition of the modulus of a complex number, k1 to n x k modulus squared. And this is true for both real and complex numbers, because for a real number, x star is the same as x. And therefore we have x squared, in which case we simply get the sum of squares. So this is norm. And that is the extension, a generalization of the notion of length to multidimensional spaces that can potentially be complex. what was previously just our 3D reality or a 2D piece of paper, we can now extend to the sorts of spaces that you will encounter when you deal with molecular orbitals in quantum mechanics. Okay, what about the angle? The most rigorous definition of angle, in fact, comes from the definition of a scalar product. If you remember, in 3D, we had x scalar product y. It was the length of x times the length of y times cosine of the angle between them. And this is what we will now generalize. Notice that we have this, and that is the scalar product. Inner product is the other name. These are the length and the norm we have already introduced. Therefore, in order to introduce the notion of an angle into a multidimensional complex space, the only thing we need to introduce is the notion of this scalar product. And in 3D, it was x1, y1 plus x2, y2 plus x3, y3. Remember, you had to multiply the two vectors element by element, and you had to add them up. So what we will now need to do is to design exactly the same procedure, but also account for the situation where the numbers can be imaginary. Okay, the real space, the one that has more dimensions than 3. The extension is quite straightforward. We put a sum around it, and that extends it to multiple dimensions. So x dot y will be a sum k from 1 to the dimension of the space x, k, y, k for the real case. Scalar product. Real. What about the imaginary one? Well, let us note here that the scalar product of a vector with itself has to be the square of the distance. So x is a sum k1 to m xk squared, necessary because of the definition above. And we remember that for the norm, we had to have the conjugate to keep it real. It's rather similar in this case because there are two norms and there's a cosine that we likewise have to be careful about. And so the definition in the complex simply inherits the definition that we have for the norm. Again, there's a more serious derivation for that called polarization relations that we don't have the time for, so I'm hand-waving here a little bit. But in the complex case, x dot y is k from 1 to m x k conjugate y k. So that is the scalar product in the case of the complex space. Again, as the case was with the norms, the complex case contains in it the real case, because if xk happens to be real, conjugation then does nothing because there is no imaginary component, and you get the real definition out of it. So in a way, the complex case is more general than the real case because it contains the real case as a special situation. Let's take a couple of scalar products and a couple of norms. In particular, an important operation in quantum theory that the second and third years have already seen is normalization, that is making sure that the vector has a unique length. So something that was pointing in a certain direction might have some length, and we would like to have a vector that points in exactly the same direction but has a length of 1. Obviously, in order to do it, we simply need to divide it by its length. And the procedure is called normalization, and it's quite straightforward. So if we have x equals norm 1, well, the length of this is obviously root 2, because x is root 1 squared plus 1 squared root 2, but you probably can simply just guess from your geometry, right, that the length of the vector that has an x of 1 and a y of 1 is root 2. So that is the norm, and so the normalized version of x will be 1 over root 2 1, or equivalently 1 over root 2 1 over root 2. If you take the square of this and the square of that and add them together, you will get 1. This is normalized. If we have a 3 by 3 vector, or let's take a complex 2 by 2 vector, if our x is, for example, 1 plus I 2, then the length of x on x is root. This squared is just 4. Then this squared, remember the conjugate, wherever that was, here. So it's 1 plus I times 1 minus I. If you multiply it out, you'll get 2. The total here is 6. So that is root 6. In order to normalize this vector, we need to divide it by root 6. In which case, it will be a vector pointing in some abstract complex direction that is by now impossible to visualize, because the space is not something that we're used to. Our brain has evolved to perceive the real space, but in some generalized space it will be pointing in the same direction, but it will have a length of 1 if you divide it by root 6. Okay, so you will encounter a lot of that in the workshop, and what I need to introduce finally is some notation that is common in physics. It was introduced by Dirac and carries his name. And this is an important notation because it is the same between vectors and functions. We are here introducing a vector space, but sooner or later these vectors will become very densely spaced and have a lot of elements, and they will become functions. And then we will have scalar products between functions, and that's the only notation that really doesn't change when that happens. And this is Dirac's notation. And what Dirac said is, why don't we replace this and start writing that x and y. It doesn't sound like a lot of difference, but you will realize in due time that this is way more convenient. This is called bracket notation. This is called bra, and that is called bracket. And they can occur on themselves. So for example, x will be 1, 2, 3, and then it's bra version with the brackets the other way around will be the transpose. 2, 3. And surprisingly enough, this is really useful. I will only just mention this, and this will really come into the front when x and y become f and g, because then you get scalar products between functions where sum becomes an integral and so on. But for now, I'll just let this notation sit, and I think your workshop contains some examples of it to get you used to it. Okay, so the summary of the lecture is we have started from basic things that I could see some people in the back seats rolling their eyes, oh no, not again, that you've clearly seen before. but we then proceeded to put some gloss and polish on it and introduce the formal notion of what mathematicians mean by a space. And it is satisfied by a surprising variety of objects. You will see some in your workshop problem set. And then we also imported, by extending it to multiple dimensions, the notion of distance and angle that we have seen in our good old 3D into the situations where we have potentially many dimensions and when we can have complex elements, so we have to play around carefully with conjugation. And with the slightly unusual bits here, the extension was straightforward, and you can see here how the complex case is a more general one than the real case, because it contains the real case in it when the conjugation operation disappears, because the numbers are real and there's nothing to conjugate. Okay, so we introduced the space, we introduced what's called a metric on that space, the norm and the scalar product, and we will start manipulating spaces in the next lecture. Any questions? Right, see you, sorry.